These are your last notes for genetics, your pedigrees notes. Let's go ahead and start. We're on page 39 of your practice packet. Almost there, so let me get my little marker out. So a pedigree, I'm just going to read with you here. A pedigree is a visual, it's a chart that shows you the relationships within a family and helps you figure out how traits are passed on, if they're dominant or recessive, if they're autosomal or sex-linked. So let's just kind of jump down here to a pedigree and just see the symbols. So circles are always females, squares are always males. If a shape is shaded in, like this square right here, that means that individual is affected by whatever trait is being shown. And it doesn't always have to be a disease. Sometimes this is something benign like eye color is being shown in a pedigree, or sometimes maybe it's color blindness, or sometimes it's something more serious like Huntington's. But all that shadedness means is that the individual expresses as a phenotype that trait. Sometimes, if the pedigree or the maker of the pedigree is kind enough to let you know, they will half shade a shape, kind of like up here with this female. A half shaded shape means that individual is heterozygous. It means they are a carrier for that trait. And finally, if a shape is unshaded, that means the individual is unaffected. They do not have whatever phenotype is being shown in the pedigree. The lines show you relationships. So these horizontal lines between two shapes are called marriage lines, but they're really reproductive lines. These two people have reproduced, and down from that, there's a line going down, and all of the individuals attached are offspring. So for instance, if this were the P generation, the parent generation up here on top, let's see, they had a daughter, they had another daughter, they had a son, and they had another son. So they had 4 children here. And then obviously people come into the family like this guy here. He married one of the daughters and then they had kids. So this is the F1 generation here in this second row, and this is the F2 generation here in this third row. And you can keep going, but you can figure out, oh, these 2 people are grandparents or aunts and uncles or cousins or all that other stuff, or brother and sister, etc. Things to remember when you're looking at a pedigree. A cross of 2 recessive individuals can never give a dominant result. I mean, these should make sense. These are not kind of mysterious things, but it's just good to go over them. 2 dominant individuals can produce recessive offspring if they are heterozygous. A dominant trait cannot skip a generation. This is a key one to look for here. If you have a trait that shows up in every generation, there's an excellent chance it is dominant. The next one here is also good to remember. Sex-linked traits are more common in males. So if you look at a pedigree and all of the squares are shaded, but really no circles are, that's a dead giveaway. You're looking at a sex-linked trait. So let's take a look at the first 3. Huntington's. Huntington's, you're going to have to remember from the previous set of notes, is dominant. Remember, it is a dominant allele and a dominant phenotype. So every shaded shape in this pedigree has Huntington's. And I would recommend starting with what you know, right? So what do we know? Well, let's give Huntington's its dominant allele, first of all. And the lowercase recessive version is the normal version. Well, we know that everybody who's unshaded is normal. And the only way to be normal is to be homozygous recessive here. So we know that this individual here is homozygous recessive, as are these 2 individuals here. They are homozygous recessive as well. And let's start up here with the father. We know that, well, he has to have at least one capital H because he has Huntington's, but he does have two daughters that are normal, which means he still must have given them a recessive allele, which means he himself must be heterozygous for Huntington's. Right? So it's kind of a logic problem. This is the way to approach these. Start with what you know and then kind of deduce everything else. So that means his son here, unfortunately, did get his father's dominant allele. Let me zoom in. There we go. But again, the mom only had recessive alleles to give, so the son must also be heterozygous. And then I think they ask you here, what is the genotype of individual A? And as drawn, individual A is not shaded, so she would be homozygous, recessive, and normal. But if they were asking you, is it possible for her to be shaded? The answer is yes. She could be shaded, and they're just not telling us. In which case, she'd have to be heterozygous at worst. But that's how you would go ahead and go about this. Oops, I don't know why that happened. Go back down here. All right, let's look at the next one. We're gonna do 3 of these. Zoom out. Oh, there, it's right here. Number 3, what's the chance that an individual A will be affected with Huntington's? All right, there we go. All right, that's why there's a question mark there. I was wondering why there was a question mark. Well, let's put both parents in a Punnett square. The dad's on the top over here, the mom is over here on the side. Again, this is a typical Punnett square. It's not sex-linked or multiple allele or anything like that. It's just the trait that we're focusing on in the pedigree is dominant, and it looks like there's a 50... Oh, what did I do? I'm not even paying attention. These are both these are both homozygous recessive here. It looks like there's a 50% chance that individual A, this daughter here, will have Huntington's. All right, pedigree number 2 shows the inheritance of attached earlobes. So not a disease trait at all. It's just another phenotype that we can look at. Attached earlobes are recessive. Carriers are not shown. This is going to be the norm. Typically, you're not going to be given the courtesy of knowing where the carriers are. You're going to have to figure it out yourself. So attached earlobes is recessive. So I'm going to go ahead and put a lowercase r for attached, and I'll say unattached equals capital R. We're actually going to look at earlobes in a lab that we're going to do in a couple days. So you'll be able to see if you have attached or not. Here we go. So we know that people that have attached earlobes are shaded. And we got 1, 2, 3 of those individuals. And attached earlobes are recessive, which means they must be homozygous recessive for those attached earlobes. So we start with what we know. And I know there are questions related to this pedigree, but I'm just going to go ahead and fill the entire thing in with you just because it's good practice. All right, what else can we figure out? Let's see. Well, we know that this guy here, individual number 2 in the first generation, is homozygous recessive, which means, let me check that I'm doing this right. Attached earlobes are recessive. Yes, so he must be homozygous recessive. Good. Well, he only has the recessive allele to give, so all of his offspring must have at least one recessive allele. And that's not his offspring here. That's another woman who married into the family, or mated into the family. Let's see. The wife up here has at least one capital R, because she's not shaded, but she could be a carrier. Is she a carrier? Well, it looks like she is because she has a daughter that has both recessive alleles. So that means that she had to give one of those to her daughter. So she is, in fact, a carrier, one of the people not shown as a carrier. And that means also that this person here must have a capital R because they're not shaded. All right, we got that figured out. Same here, not shaded, so must have a capital R. These two, again, not shaded, so they must also have at least one capital R. But it does look like, since this person is homozygous recessive, the mom right here must have had a lowercase r, a recessive allele, to give. Let's see. So the only question here is this person right here, individual number 1 in the 3rd generation, could be homozygous dominant, or they could be heterozygous for their unattached earlobes. It's not clear because both are possible given the information in this diagram. So that's the only ambiguity here. So if we zoom out, let's see, which parent in generation 1 has attached earlobes? Well, that's individual number 2 right here. How many children do the parents in generation 1 have? They have 3 children. Remember, this person over here does not count. They're not attached to this line. Which children in generation 2 have attached earlobes? Individual number 1 right here. Which child in generation 2 is married? Again, married, quote unquote. Number 3, does this child's spouse have attached earlobes? I keep forgetting which one's attached. No, she does not. They are unattached because she is not shaded. Do any of these child's children have attached earlobes? Yes. Individual here, right, number 2. Yes. All right. There's a decent chance that I misread that and made a mistake here, but check me out. I think these are good to go. And let's go to the next one. All right, hemophilia. There we go. Here's the pedigree over here. I'm just going to go ahead and zoom right in. Remember that hemophilia is a sex-linked trait, so the very first thing I recommend is putting your chromosomes on everyone in your pedigree right from the start. Just do it. Get in the habit of it. It's a little bit work up front, but it will pay off in the problem itself. So here we go. All right. Well, we know that if you're shaded, you have hemophilia, and let's start with the men because you know that their one copy of the allele must be recessive. I'm going to use the letter N. So this person down here also has the letter N. And I could pretty much tell this is a sex-linked trait right from looking at the pedigree because only the men are affected. That's quintessential, typical sex-linkedness, sex-linked trait. So they were nice enough actually here to give us the carriers, but I think you should be able to figure out whether these are carriers or not, even if they weren't shaded. Let's see, the men here, since they're normal, let's just do all the males first. They have to have a normal copy of this allele. All right, so now it's just the females. Let's actually start down here in generation 3 and see if we can work backwards, see if we can work up. All right, so this male right here has a diseased allele that he must have gotten from mom, right? Which means mom must have been a carrier, which we can confirm because she is half shaded. But she is not full shaded, so her other allele must be normal. Let's see, that means her father, this individual right here, number 3, must have given her his X chromosome with the normal copy. This individual is not shaded, so we do have to take advantage of just knowing that and say that this allele must be dominant. Otherwise, they would have shaded this shape a little bit, and it would have been half shaded. So she is homozygous normal. All right, let's start up here. So we know that this father, individual 2, gave all of his daughters his X chromosome with the disease allele on it, the recessive allele. So at least one of these is recessive. And let's see, again, she is not fully shaded. And again, she actually is shown. They're showing you that she's a carrier, so we know that that's a normal copy. And let's see, can we do mom? See, what must mom be? Well, she herself is normal, so she must have at least one capital allele, a dominant allele. Could she be a carrier? Let's look. She could be a carrier if carriers weren't shown, because her daughter could have had the dominant allele from mom and the recessive allele from dad. So it's possible, but because they are showing us carriers here, you can infer that this must also be a dominant allele. And that's everyone here in this pedigree. So again, start with what you know, work backwards, make sure that you draw your sex chromosomes, don't forget those. Remember, in every pedigree you have 2 things to think about right up front. Is the trait sex-linked? Yes or no? And is the trait dominant or recessive? Right. So what kind of gene causes hemophilia? Sex-linked, again, that's on the X chromosome. For the trait being individuals 2, 1, and 2, 4. Let's just go through this together. 2, 1, and 2, 4 are carriers. What is the relationship between individual 1, 1 and individual 3, 2? 1, 1 and 3, assuming this is 3, 2 right here. Grandmother and grandson. That's what it looks like to me. Grandmother and grandson right there. Last one, if individual 3, 2 marries a person with the same genotype as individual 1, 1. So I'll put someone over here. And that person was homozygous normal. Whoa, okay. Homozygous normal, 0, but let's just go ahead and do the Punnett square. It doesn't matter if the male has the recessive allele because the female has nothing but dominant normal alleles. So in every single instance, they will have a normal child. The females will be carriers. Oops, I made a mistake here. This should be a lowercase n. We'll zoom in on that. The females will be carriers, but they will still be normal. And the males will be completely normal. So what is their chance of having a child with hemophilia? 0. So I hope this helped. You guys can keep doing the rest, and I will see you in class.